What we really want to do is getting space radiation, these particles from the sun, identify the origin of the particles that were detected at Ulysses. So basically we're talking about particles at high energy, and Ulysses has 19 years of data from such particles. So what you're trying to see is to identify at the sun all the events that were seen by Ulysses. So these particles that Ulysses sees are very important because they have very high energies. So these high energies particles, they can cross shieldings in spacecraft. They can cross the vests of astronauts that are in space. So these can be lethal both to humans, like astronauts in spacecraft or on the moon or outside of the Earth's magnetosphere, or they can also be lethal to technological systems like satellites in orbit or missions that we have on other planets that are not protected like the Earth by the magnetosphere. So it's important that we can predict the arrival, or you can predict the consequences or the characteristics of this kind of particle emissions. Our goal is eventually to see something at the sun and say, okay, we see this at the sun. With the spacecraft that is like in the asteroid belt, we'll see this event in 300 minutes, 400 minutes, or the astronaut is at the moon, you'll have this many minutes to get to a shelter, or someone that is at Mars or in traveling to Mars will have this time to get ready and protect, because you will experience this much amount of radiation. So our goal is to use what you're doing now to predict the amount of radiation that they will have. To reach that goal, we still really need some fundamental questions to be solved in particle acceleration. We need to know exactly where the particles are accelerated back at the sun. That is something that we still don't know. So I've taken care of the propagation part. Now we need to look back at the sun and what accelerates the particles and how accelerates and how many of them will accelerate.